Friends, in this video we'll discuss some problems related to types of relations. Let me start with an example. You do it from the exercise number 1 of your textbook. The first question is, determine whether the following relation is reflexive, symmetric or transitive. You are given a particular relation defined on the set A. What is the set A? A is the set containing the natural numbers 1, 2, 3 up to 14. R is defined as xy such that thrice x minus y is equal to 0. Okay, so you have to find the pairs satisfying this particular condition. You know how to find it? In the roster method, R will be equal to, see, you can see it is 1, 3, means if x is 1, y must be 3, x is 2, y is 6, x is 3, 9, 4, 12, like this. You know why is it not 5, 15? Because 15 is not there in the set. Okay, you have to stop it there. Only 4 pairs of elements will be in R. Now we have to check whether it is reflexive or not. So remember, you remember the condition of reflexivity. It is nothing but every element of the set must relate to itself. That means 1 must relate to 1, 2 must relate to 2, like this. But here we see that 1 is only related to 3. Just like it, 2 is also with 6 only. That means 1, 1, 2, 2, 3, 3, those are not there. Therefore, it is not a reflexive relation. So how to write it? In this way. It is not a reflexive relation. Number 2 is to check whether it is symmetric. See, now R is not symmetric because I told you earlier that if you were to show something is not, it is like not symmetric, so you can put examples. So example is 1, 3. We're taking the example of 1, 3. 1, 3 is there in R, but the converse, that is 3, 1 is not in R. You can see 3, 1 is not in R. Therefore, it is not symmetric. If any one pair is in such a way that the converse is not there in the set of R, then that R is not a symmetric relation. Okay. What about the transitivity? To check the transitivity, we always take 2 pairs such that one element is in common. Here 3 is in common in the 2 pairs. So 3 in the first pair, 3 is the second element, in the second pair 3 is the first element. So by transitivity, 1, 3 and 3, 9 are there, therefore 1, 9 should be there. But you can see in R there is no 1, 9. 1, 9 is not there, therefore it is not a transitive relation. It is not a transitive relation. Okay. Number 2, we consider a particular example of some natural numbers n. Okay. Here you can see R is defined as x, y, such that y is equal to x plus 5. Y is equal to x plus 5, where x should be less than 4. Means x belongs to n, means natural numbers, therefore x must be 1, 2 and 3 only. By putting x, the values of x as 1, 2 and 3, what we get? We get the values of y like this. That means R becomes 1, 6, 2, 7 and 3, 8. Now you see, first of all, R is not reflexive because 1, 1 is not there, 2, 2 is not there, and 3, 3 is not there. Therefore, R is not reflexive. Similarly, R is not symmetric. As I told you earlier, we put an example here. 1, 6 is in R, but 6, 1 is not in R. Therefore, it is not symmetric. Then come to transitivity. Now you can see there are no two pairs which have one element in common in R. No 2 pairs. Therefore, we cannot check whether it is transitivity condition is satisfied or not. Therefore, we say that it is a transitive relation. Okay. Now proceed to the next one. It is an example from your book. A relation R is defined on the set of integers, it is Z, as R equals to xy such that x minus y is an integer. Okay, x minus y. If the difference of two integers becomes an integer, then that two integers will relate to each other. Now the first thing is that the difference of x from x is equal to 0, and we know that 0 is an integer. Therefore for all x we'll have x minus x equal to 0, which is an integer. Therefore x will relate to x itself. And how we write it? X belongs to R for all x belongs to Z, and that will mean that it is a reflexive relation. Okay, again let xy belongs to R. That means a pair, we consider a pair xy from R. Then by the definition of R, x minus y must be an integer. Now if x minus y is an integer, then x minus y belongs to Z, and that will imply that minus y minus x must also be in R. We are just taking common that minus sign. Now what can I do? If minus y minus x belongs to Z, then y minus x must also belong to Z. Okay, because we know that if 5 is an integer, then minus 5 is also an integer. Just like that, minus 10 is an integer, then 10 must also be an integer. In that way we can say that y minus x also belong to Z, and that will imply that yx belongs to R. Now by taking xy belongs to R, we have got yx belongs to R. That means it is a symmetric relation. For the transitivity, we consider two pairs xy and yz from R, where y is the common element. Now if xy belongs to R, that will mean that x minus y belongs to Z, means x minus y is an integer. Similarly yz belongs to R, therefore y minus z is an integer. Now x minus y plus y minus z, that means sum of two integers, is equal to x minus z, which must also be an integer. And that way we can say that xz belongs to R, because x minus z belongs to Z, therefore xz belongs to R, and that gives us that R is a transitive relation. Here you can see that all the three conditions of reflexivity, symmetricity and transitivity are satisfied in this relation. Therefore R is an equivalence relation. Let me proceed to the next problem. Suppose there is a problem, show that the relation R in the set R of real numbers defined as R equals to AB such that A is less than or equal to B square is neither reflexive nor symmetric nor transitive. Okay, this time we are considering the set of real numbers, not the set of integers only, the set of real numbers, means A, B and all these are real numbers this time. Here the solution will be like this: R is equal to AB such that A is less than or equal to B square, means the first element is less than or equal to the square of the second element, where A, B are real numbers. Now for all real numbers A is less than or equal to A square is not true. It is not true. We can show it by putting examples just like this. Consider the real number half. Half it belongs to R. But what is the square of half? The square of half is 1 by 4. Therefore half is not less than or equal to, the sign should have been not less than or equal to half square. An element A relates to the second element if it is less than or equal to the square of the second element. But half is not less than or equal to half square. In that case, we can say that means half is not related to half, so R is not a reflexive relation. Now you see 1, 2 belongs to R because 1 is less than or equal to 2 square. We can consider 1, 2 to show that it is not symmetric, because 2, 1 is not in R, because 2 is not less than or equal to 1 square, and that gives us that R is not a symmetric relation. For transitivity, we consider 2 pairs of elements from R. The first pair is 5, 3. 5, 3 belongs to R as 5 is less than or equal to 3 square. 3 square is equal to 9 and 5 is less than or equal to 9. That is true, therefore 5, 3 belongs to R. Similarly, 3, 2 belongs to R as 3 is less than or equal to 2 square. 2 square is equal to 4, so 3 is less than or equal to 4. Therefore 3, 2 belongs to R. Now 5, 3 belongs to R, 3, 2 belongs to R, here 3 is the common element, therefore we must have 5, 2 belongs to R. But 5 is not less than or equal to 2 square, which will give us that 5, 2 does not belong to R. That means 5, 3 belongs to R, 3, 2 belongs to R, but 5, 2 does not belong to R. That means R is not a transitive relation. That completes the problem. Let me give you a homework. You write down this particular problem. Here, similar to the earlier one, a relation R is defined on the set R as AB such that A is less than or equal to B square. So B cube, you have to show that it is neither reflexive nor symmetric and nor transitive. You may proceed as earlier. Let me give you one more, that is show that the relation R in the set A of all books in a library of a college given by R equals to XY such that X and Y have same number of pages is an equivalence relation. You try to show this. In the next problem, we have to show that the relation in the set A of points in a plane given by R equals to PQ such that the distance of the point P from the origin is same as the distance of the point Q from the origin to be an equivalence relation. We need to show that the above relation is an equivalence relation. Now you can see here R is nothing but pair of points on a plane such that the points will relate to each other if the distance of them from the origin are equal. Just like P and Q relates to each other if OP equals to OQ. O is the origin, so O is the origin. So you can see on a plane we can consider X and Y axis and some points just like in the diagram P, Q, R. These are at equal distance from the origin. Therefore, by the definition of R, what we see, P will relate to Q. Okay, and P will relate to R also because their distance from the origin are same. Even Q will relate to R. Okay, these 3 points P, Q and R are related to each other. But you can see S is not as S is not at the same distance from the origin as P, Q and R. Therefore S is not related to any of these 3 points. So this is the diagram actually. You can see how to prove it. Now PP belongs to R as OP equals to OP. Distance of P from origin is equal to the distance of P from origin. You can consider in that way every point of that plane will relate to itself. So therefore it will be a reflexive relation. It is easy to show that. For the symmetric property, we consider a pair PQ from R. Okay, suppose PQ belongs to R, then OP equals to OQ, means distance of P from the origin must be equal to the distance of Q from the origin by the definition of the relation. Now can say we can also say OQ equal to OP. If OP equals to OQ, then we can say OQ equals to OP, and thus it means that Q and P are related to each other, just like QP belongs to R. So thus we get PQ belongs to R implies QP belongs to R. So R must be a symmetric relation. Now for the transitivity property, we consider two pairs of points. The first pair is PQ belongs to R, and that will mean that OP equals to OQ, and QR belongs to R. Here P, Q, R are 3 points on the plane. Since QR belongs to R, therefore OQ must be equal to OR, means distance of Q from the origin is equal to distance of R from the origin. Therefore we can write OP equal to OR, because OP equal to OQ, OQ equals to OR, therefore OP equal to OR, and thus PR belongs to R. P and R, these 2 points are related to each other. So by definition of transitivity, it is a transitive relation, and since these 3 conditions are satisfied, therefore we can say R is an equivalence relation. Consider the next problem. Show that the relation R defined on the set A of all polygons as R equals to P1 P2 such that P1 and P2 have same number of sides. You know, polygons, the set of polygons include triangles, quadrilaterals, pentagon, hexagon, heptagon, and all those. Therefore P1 P2, these are polygons on a plane, and R is the relation such that 2 polygons will relate to each other if and only if number of sides of them are same. So we need to show that R is an equivalence relation. See, the solution is just like this. A is the set of all polygons, R is defined in that way. You can see 2 triangles will relate to each other. 2 triangles. Why? Because number of sides of a triangle is 3, and since it has to be equal, therefore a triangle will relate to a triangle only. A triangle will never relate to a quadrilateral, because quadrilaterals will have 4 sides. So 2 triangles will relate to each other, 2 quadrilaterals will relate to each other, and in a similar way you can see these triangles will relate to each other because they have same number of sides. These quadrilaterals will relate to each other because they have same number of sides, and also the pentagons will relate to each other. What may be their shapes, but sides are same. Okay, let P belongs to A, means P is a polygon, then P has same number of sides as P itself. If P is a triangle, then it has 3 sides and it will relate to itself because equal sides are equal, number of sides are equal, therefore they will relate to each other. Means every P will relate to P where P is any polygon. Thus R is a reflexive relation. Again consider two polygons P1 and P2 such that they relate, means P1 P2 belongs to R. It may be triangle, it may be quadrilateral or anything, any polygon. I mean to say that if P1 is a triangle then P2 has to be a triangle. Therefore number of sides of P1 is equal to number of sides of P2 because P1 relates to P2. We can write it in this way also. Number of sides of P2 is equal to number of sides of P1, and that will mean that P2 P1 belongs to R. If P1 is related to P2 then P2 is also related to P1, hence R must be a symmetric relation. And then the next one, for the transitivity you consider two pairs. Suppose P1 is related to P2 and P2 is related to P3, you write it in this way. Therefore P1 and P2 have same number of sides. P2 and P3 must have same number of sides. So can we conclude that P1 and P3 have same number of sides? Because P1 and P3 have same number of sides, therefore P1 P3 belongs to R. So what we get, if P1 P2 belongs to R and P2 P3 belongs to R, therefore P1 P3 belongs to R. So hence R must be a transitive relation, and consequently we can say that R is an equivalence relation. Okay, you try to solve other problems from your exercise, and let me give you one more concept right now. It is called equivalence class. What is an equivalence class? You see, given an arbitrary equivalence relation R in an arbitrary set X, R divides X into mutually disjoint subsets AI called arbitrary equivalence partitions or subdivisions of X, satisfying the following properties. All elements of AI are related to each other for all I. No element of AI is related to any element of AJ where I not equals to J. The third one is the union of all AIs must be equal to X, where AI intersection AJ is equal to pi. That means all AIs are mutually disjoint. In that case, the subsets AI are called equivalence classes. We'll get to it in the next video. You see the next video for this one. Okay.